Time lapse. 127 feet later.
Hi, my name's Heather. I'm a geophysicist at the Geological Survey of Canada. Today we're at the Bells Corners Borehole Calibration Facility. It's a facility that was developed by GSC research scientists in the late 1970s. And for the last 40 years, it's been used by members of industry, government, and universities to calibrate their downhole geophysical equipment. After a tool is calibrated here, the tools go off to project sites all over Canada, where they can be used for mining, geotechnical, or environmental projects. So right now we're in the first part of the calibration facility, which is the deep bedrock borehole test site. A borehole is just a cylindrical hole in the ground that's often filled with water, groundwater. And to make them permanent installations, we'll put a casing in the top to prevent any debris that's loose from falling inside the hole. Borehole geophysicists will lower different geophysical instruments into the boreholes to measure different properties of the rock. There are 6 different deep bedrock boreholes here. They range in depth from 75 to 300 meters, and they intersect the main rock types of the Ottawa area. When we're here at the facility, we'll lower our tools down these boreholes and we'll measure different properties of these different rock types. The rock cores are kept from each of the 6 boreholes. Those rock cores are available to anybody who wants to come and study them, either to learn more about the geology in the Ottawa area or to make measurements on the rock cores to compare to their downhole geophysical tools. We do compare the rock cores to what we see in the borehole. We can record the inside of the borehole wall with high-resolution cameras, and then we'll compare that to what we see on the bench with the cores. The borehole almost provides a little bit of a window for us to look into what's happening in the bedrock below our feet. Another important aspect of the work we do at the calibration facility is trying to better understand groundwater and how it flows through the bedrock. The GSC is working on several different projects with university collaborators to better understand how groundwater is flowing through the bedrock to try to protect and conserve groundwater resources. So this is a flow meter tool, and it measures changes in water flow and direction based on a heating grid that's located in the center of this wire mesh. Any water that's naturally flowing in the borehole is forced through this wire mesh. And so when we trigger a heat pulse from the center of the tool, this warm lens of water is either pushed up past the thermistors, or if water's flowing down in the borehole, it's pushed down past these thermistors. And we can detect the rate at which that heated lens of water is moving and assign a flow value to it. So we know the direction that water's moving in the borehole and also the rate of flow. So in the last couple of years, we've also installed a small weather station to measure precipitation levels and changes in air temperatures. So we're in the second part of the calibration facility now, and this is what makes it truly unique, because it's only one of 2 sites of its kind in North America. We're standing on top of 9 concrete calibration blocks. Each of these columns was constructed to simulate natural variations in the rock-forming elements potassium, uranium, and thorium. The minerals that make up rock can have different concentrations of these elements. Calibrating our tool responses in each of these columns lets us identify changes in rock type and also even identify the concentration of some economic minerals when we're logging real boreholes. We use this facility to calibrate spectral gamma ray tools. Spectral gamma ray tools measure naturally occurring gamma radiation in rock. Each of these columns is 4 meters in height. The bottom is concrete. The center block mimics conditions in the real world, in a borehole, and the top portion again is just concrete. The value of a site like this is that it allows people the chance to calibrate their instruments not only across time, but also across different logging systems, so that at project sites where a lot of data have been collected over the years, they can be integrated together into a larger study, knowing that the instruments have been calibrated to a common standard. A site like this also gives us a place where we can study bedrock properties and monitor groundwater over the long term, so that as technology and methods advance, we can continue to build on over 40 years of geoscientific research and development here at the facility.
Okay, good.
If you like this video, let us know with a thumbs up. Click on the logo below to subscribe to the Simply Science channel and click the bell icon to be notified when we upload new videos.